Harmonic analysis of non-sinusoidal waveform. Non-sinusoidal means rectangular, square, triangular, sawtooth. Like this, these are the waveforms are called non-sinusoidal waveforms. Under this, I'm taking one example that is called rectangular waveform. By taking rectangular waveform, here we have to investigate the harmonic analysis of non-sinusoidal waveform that is called rectangular waveform. First, under this, one of the main important concept is called total harmonic distortion, that is called THD. THD is called total harmonic distortion. It is the ratio of sum of harmonics to the fundamental signal component. It's called as a total harmonic distortion. Okay, generally it is up to 5 to 6 harmonic components are generally to use for calculation of THD. 5 to 6 harmonic components are generally used for calculation of THD. That is called fifth harmonic or sixth harmonic or ninth harmonics also. Okay, in other words, this total harmonic distortion is defined as the ratio of RMS of fundamental signal to the mean of root sum of squares of its harmonic pulse. All noise components or voltage components is called as a total harmonic distortion. This is the mathematical representation of the total harmonic distortion, how to calculate. For measurement of power, so this that is are in powers. So we can write formula like this: total harmonic distortion is equal to under root of P2 plus P3 plus P4 plus 4 Pn divided by P1 into 100. That is in terms of powers. In terms of voltages, the data is given like this: voltages, measurement data in volts. So to calculate this total harmonic distortion is called under root of V2 square plus that is called second harmonic, third harmonic, fourth harmonic voltage squares of V2 square plus V3 square plus 4 V4 square plus so on Vn square divided by fundamental V1. Okay. So like this, we can calculate the total harmonic distortion of non-sinusoidal waveform. Then coming to the, so by taking the one example, rectangular pulse, this is called rectangular pulse. In this rectangular pulse, this is called Fourier series expansion. So Bk is equal to 0 for k is even, Bk is equal to Fourier by pi k for k is odd. Okay. Then Fourier series expansion is called f of t is equal to Fourier divided by pi into sin omega t fundamental, then 1 by third into sin 3 omega t, third harmonic 1 by 5 sin 5 omega t, fifth harmonic 1 by 7 sin 7 omega t. This is called seventh harmonic. Like this, this is called Fourier series expression. Here, in this expression, Bk is equal to Fourier divided by pi k for k is odd. For different values of k, we will find B1, B2, B3 like this, B1 harmonic voltages. Okay, by taking the A is equal to 30, T is equal to 0.01 seconds, F is equal to 1 by D, that is called 1000 seconds, 1000 edges. That is called 1 kilo edges. Center frequency is called 1 kilo edges. Then here, B1 is equal to 38.1732, 19732 means here, substitute A is equal to 30, K is equal to 1, and pi 22 by 7, then R K is equal to 1. That is called fundamental harmonic voltages, 38.1972. And similarly, B3 by substituting the K is equal to 3, same as it is A is equal to 30, T is equal to 0.01. In this, A is equal to 30, 4 pi is equal to 22 by 7. Like this, substituting these values of different values of K, so we will get fundamental harmonic voltage, third harmonic voltage, and fifth harmonic voltage, and seventh harmonic voltage, ninth harmonic voltages. Like this, these are the different types of harmonic voltages. Substitute in this formula, third harmonic total harmonic distortion formula. Here, by substituting the values of second harmonic voltage, that is called 12.7324. Okay, the next 7.6394 volts scale. The next 5.456 scale. Then 4.244 is scale like this by fundamental 38.1972 scale into 100 in terms of percentage. Then total harmonic distortion is called 42.877%. This is our total harmonic distortion of rectangular pulse. So for these calculations, A is equal to 30 volts and K for different values of K. And so like this, we will get the total harmonic distortion theoretically. Then we have to verify by using PSPICE. Okay. So PSPICE, first we have to generate this Kerr waveform. First, we have to generate the rectangular waveform, not square waveform. Peak amplitude A is equal to 30, positive amplitude is called minus 30, plus 30, and V1 is called minus 30, and V2 is called plus 30. Like this, we will get generate a rectangular waveform. And here, by taking the values of delay time, TD is called delay time 0 seconds, rise time 1 microseconds, fall time 1 microseconds, pulse width is equal to 0.5 milliseconds, pulse repetition, PER is called pulse repetition is called 1 millisecond. Here 0 label is called 0 and is called 1, and this square waveform is called V pulse. By placing the V pulse and taking one resistor here, then we will get voltages, waveform, rectangular waveform. Like this, rectangle waveform can be generated by using this values. Okay, then coming to the next settings analysis, transient analysis. Print step 2 milliseconds, final time 5 milliseconds, and enable like this, enable Fourier series, and then center frequency 1 kilohertz, number of harmonics called ninth harmonics. Output varies across V of 1. So this is called 1. That's why we have to write 1 V of 1. And then next simulate. By simulating the light, we will get like this Fourier spectrum will be displayed, and these are the different types of fundamental harmonic voltages. And then next we will get this total harmonic distortion theoretically. So this is about theory about finding the total harmonic distortion. Then coming to the how to execute this experiment with practically by using PSPICE, open PSPICE schematic. Okay, open PSPICE schematic. Like this, open PSPICE schematic, and take V pulse, V pulse here, right here. This is called new partner. Go to new path, draw, get new path. Right here, V pulse, V pulse, V pulse. Place here. This is called V pulse symbol, V pulse. Okay. Then next, take one resistor, resistor. Press Ctrl R like this, and connect this uh, circuit. Change the resistance is equal to 100, 100 or 1K, whatever it may be, we will get these results. And this is called voltage marker. Voltage marker. Press this voltage marker, place here, and right here label is called 0, 0 label, and this label is called 1. Press 2 times and then open like this, and here DC is equal to 0, DC is equal to 0, AC 0, AC 0, and V1 is called minus 30, minus 32 plus 30. The waveform is changes, minus 30. V2 is equal to plus 30. V2 is equal to plus 30. And delay time is called 0 seconds. 0 seconds. And rise time is called 1 microseconds. Rise time 1 microseconds. US. And then next TF is called fall time. Fall time is also same as the rise time. Fall time is also 1 microseconds. Rise time, fall time both are same. And pulse width PW is called pulse width. Width of the rectangular waveform 0.5 milliseconds. 0.5 milliseconds. Pulse width is equal to 0.5 milliseconds. Then PER is called pulse repetition. Pulse repetition is called 1 milliseconds. After 1 millisecond, the waveform is repeating. That's why it's called as a pulse repetition, PER. And then take one ground place here. Okay, like this. So simulate, save before going to simulate and save. And also one more point is that is called analysis, HD. Okay, analysis. Generally, waveform is generated with Fourier series. Okay, go to analysis, setup, enable transient and open transient, and print step is called 1 milliseconds, and here 5 milliseconds. Final time is called 5 milliseconds, and enable Fourier series. This is very important. These settings enable Fourier series, and they are Center frequency is called 1 kilohertz, and the number of harmonics is called 9, and output varies in terms of brackets. V of 1, V of 1, we have to write like this, we have 1, and then okay, close, and then simulate. Rectangular pulse will be generated in this way. This is called our rectangular pulse waveform, rectangular waveform. Okay. So for this rectangular waveform, here icons, so this is called zoom, and zoom in, zoom out, and zoom to fit, and this icon is called FFT, fast Fourier transform, fast Fourier. Okay, this icon, fast Fourier series. Press this icon, and this power spectrum, harmonic spectrum will be displayed. So in this harmonic spectrum, mark label here. Press this toggle cursor and mark label, and here mark a peak, and mark label like this 38.348. It will be display as it is, whatever the values here, 38.143. In the same way here also, same theoretical and practical values display, and then mark label. So 11.72 next, so mark label like this for this power spectrum, different of some harmonic voltages, label and take print, place on record. So like this, power spectrums will be display, harmonic spectrum or power spectrum will be display, and then after that, the first icon is called view circuit file, and second is called view simulation output. View simulation output. Press this view simulation output, and here you will get the start total harmonic distortion. Practically, this is called our total harmonic distortion. So here, total harmonic distortion 4.302 into 10 to the power of 1 is called 43% total harmonic distortion. Okay, this is about the total harmonic distortion, to calculation of the total harmonic distortion of a rectangular pulse. Okay, understood? First, must open PSPICE schematic. Okay, first open PSPICE schematic. Go to new path, plus VPulse, open PSPICE, place here, and open VPulse, and AC DC0, AC0, V1 minus 30, please V2 plus 30, and delay time 0 seconds, rise time 1 microseconds, fall time 1 microseconds, pulse width 0.5 milliseconds, and the pulse repetition is called 1 milliseconds. Like this, enter the values. Okay. So rise time, fall time is very less in rectangular pulse. That's why microseconds. Pulse width is more, and pulse repetition is called time period of the rectangular waveform. That is called 1 milliseconds. And then it close, and here and under label, interlabel like this 1, and here also label 0. Then after that, go to analysis, setup, transient, enable transient, print step 0, 1 milliseconds, final time 5 milliseconds. Okay, enable Fourier series is very important. Enable Fourier series. This point, this mark is compulsory. Enable Fourier series. Okay. Enable Fourier series, and center frequency 1 kilohertz, and the number of harmonics is called 9, and output varies is called V of 1. V of 1, then okay, and press okay, close, and simulate, and harmonic right, like this. Rectangular pulse will be generated. So after this rectangular pulse, here this icon is called Fourier. Okay, Fourier icon, this icon, Fourier. Press this Fourier icon, and this spectrum, harmonic spectrum will be displayed in this way. Okay, so mark labels by pressing this toggle cursor. Mark labels here respect to points. Okay, and then next in this way, mark labels and take printout and place in record. Okay, and then next, first icon is called circuit file, And second icon is called view simulation output. Press this icon. Okay, simulation output. Press simulation output, then go to last one. This is called total harmonic distortion. Okay, calculations with the results here. This is called 4.32 into 10 to the power of 1, 43.02%. Like this, we can calculate total harmonic distortion, and we can find the by using PSPICE practically. Okay, so for this, and also triangular waveform also can be find total harmonic distortion practically and theoretically by using Fourier series expression. Okay, for triangular waveform and sawtooth waveform, remaining circuits are assignments for you. So in lab, practice this experiment and place and record.